Welcome back to the playlist on amino acid catabolism. Sorry, that was my email. We're still talking about histidine, and we're talking about histidine catabolism. And in this pathway so far, we've seen a lot of strange enzymes. We've seen a lot of strange mechanisms. And this enzyme is going to be no exception. This enzyme is urocanate hydratase. And it's a very bizarre mechanism because it's going to use NAD in a very bizarre fashion, and we'll talk about that in a few minutes. But right here, the structure right here that looks like histidine, or at least it looks like part of histidine, is urocanate. So that molecule right there is urocanate. It still has the imidazole ring, right? And the imidazole ring is going to behave a lot like it did in the previous mechanism of histidine ammonia lyase, except for the fact that the electrophile is not the methylidine imidazolone. Okay, that's not our electrophile in this case. Our electrophile is actually going to be NAD. Let's think a little bit about NAD, nicotinamide adenine dinucleotide. When we look at NAD in other videos, what I want you to realize is that in every video that we've seen up to this point, and in every other reaction that you've seen of NADH, it's carrying electrons in the form of hydrides, right? If you were to look at the hydride, it's just a hydrogen atom with 2 electrons with a negative charge, right? That's what it's carrying in the form of NADH. So when we look at the mechanism of NAD-dependent oxidation, or when we reduce NAD to NADH, and certainly go back and review the video on that. When we do that, NAD is going to be the electrophile, and NAD ordinarily is an electrophile, right? That's its function, is to accept electrons, right? So in other words, we could say it's a Lewis acid. It's a Lewis acid because it normally accepts electrons from the Lewis base, which is pretty much always a hydride. And up to this point, that's all we've seen it as. But in this video, and this is the first time we're going to see this, the actual nucleophile that's going to attack the NAD ring is actually not a hydride. It's actually a carbon atom. And specifically, it's going to be in the form of a carbon with a negative charge. Okay, this is very strange, and you pretty much, for the most part, not really ever see this again in Biochem 1 and 2. This is a very unique mechanism, and so let's explore it now. And one thing I will do, just for the sake of space, when I abbreviate R prime, that's essentially this amide up here, and the rest of the molecule is R. Okay, and that's, again, just for the sake of space. I don't want to have to draw that whole thing out every single time. Okay, the nicotinamide ring, again, just like in the case of hydride transfers, is the only functional part. Okay, so the initial step in the mechanism is going to be nucleophilic attack on this carbon right here. So it's just like it was in the case of hydrides, except this time it's actually going to be a carbon that attacks. So we're going to have this lone pair kick in here to form a pi bond, and this pi bond comes out and attacks the nicotinamide top carbon. And that's going to force these double bonds to rearrange such that the terminal pi bond is a lone pair on that nitrogen. Okay, so we saw that, and I'm going to actually do the rest of the mechanism in green because that's how I've been doing it. And also I have this proton in purple. Okay, so there's a base in the active site, and the base is going to deprotonate this carbon right here. It's going to transfer this proton, and in the process, it's going to cause the formation of an alkene right here, and that's going to force these pi electrons onto this nitrogen. Okay? So at this point, what we've done in the first step is we destroyed the imidazole ring, right? We destroyed aromaticity, but we've gotten it back. We've gotten it back in this mechanistic step, right? Okay, so we've gotten it back. Now something's going to happen that's very interesting. Something very interesting is going to happen. This next mechanistic step is not something that you would ordinarily see in biochemistry. In fact, the only other reaction that I'm aware of that does this off the top of my head is a non-enzymatic reaction. And if I say non-enzymatic reaction, the first thing that should come to your mind is vitamin D activation. And the type of reaction this is going to be is called a sigmatropic rearrangement. Very rare type of reaction. The vitamin D sigmatropic rearrangement was spontaneous. This sigmatropic rearrangement is facilitated by the enzyme. Okay, so what's essentially going to happen is a concerted electronic rearrangement. And I'm drawing this in a particular order, but just know it's not in a particular order. All three of these electron movements are concerted. So you'll have the hydride is going to come and attack here. This pi bond is going to rearrange to right here, and then this pi bond is going to come here. Okay, and this process where we have this 6 electron rearrangement, this is called a sigmatropic rearrangement. It's a type of paracyclic reaction. And certainly you can go back to your organic chemistry and review that. And it should be in the conjugated pi system chapter. Okay, it's a sigmatropic rearrangement, very rare. Like I said, the only other one that I can possibly think of that you might have seen is in vitamin D activation to cholecalciferol. Other than that, we really don't see them. Okay, and as a result of the sigmatropic rearrangement, we get this guy right here. Okay, now what's going to happen is this lone pair is going to kick in here to form a pi bond, and that's going to cause these electrons to come here and rearrange that pi bond, and then these pi electrons are going to come and reabstract the proton. Okay, they're going to reabstract the proton. Okay. And that's going to give us this guy right here. Now, at this point, this is where the addition reaction is going to occur. If you remember from the last video when we did a histidine ammonia lyase, I mentioned that the overall reaction of urocanate hydratase was an addition reaction. And this is going to be the step in which we're going to see the addition. Okay, so another base in the active site is going to deprotonate water. And the effective hydroxide is now going to attack this carbon right here. And as a result, there's going to be an electronic rearrangement. This pi bond goes here, and these pi electrons come out onto this nitrogen to make the amine. Okay, and as a result, what we've effectively done is we've hydroxylated what was urocanate. And keep in mind, we still have NAD there, okay? So basically what we're going to go about doing now is we've somehow got to get rid of the NAD ring, and the next few steps are going to be what accomplish that. Okay, so the very next step in the mechanism is going to be these electrons right here. They're going to kick in and form a pi bond here, and that's going to result in these electrons coming out and abstracting this proton, right? And it's going to regenerate the resting state of that base. So we still don't have the imidazole ring, and in fact, we're not going to have the imidazole ring at the end. And that proton transfer is going to yield this guy. Now we still have the NAD ring attached, and at this point, this is going to be where the NAD ring dissociates, okay? And I'll do this in a bold color. I'll do it in red. So these pi electrons are going to kick in here, and you're going to get the same double bond rearrangement that you would normally get when NADH does a reduction or NADPH does a reduction. It's the same mechanism, except instead of expelling a hydride, we're expelling this, what was urocanate, and what is effectively going to be imidazolone propionate. Okay, and so what that does is it causes these electrons to kick in here, and by the way, this should have a positive charge, and that's going to cause these pi electrons to kick up onto this nitrogen. Okay, so now we have NAD plus back, so we've kicked off that ring, and now what we have is we have the enol version of something called imidazolone propionate. We have the enol version of imidazolone propionate, and you can imagine that this molecule spontaneously is going to quickly tautomerize, and it's going to. And the tautomer of the enol is just going to be a carbonyl, okay? And that carbonyl is characteristic of this molecule, which is imidazolone propionate. Imidazolone propionate. And I have a question for you, and I encourage you to pause the video. And the question is this: what is the driving force for the equilibrium being so far favored in this direction? What's the driving force? And I'll give you a minute to pause the video and see if you can figure it out. And I'll assume that you've had a go at it. And the driving force for this spontaneous tautomerization is the fact that these enols are terribly unstable. Remember back to your organic chemistry, enols are very high energy, very unstable. And remember, let's take, for instance, acetone. So let's use acetone as an example. So at any time we have acetone here, and acetone doesn't always exist in that form. Now the equilibrium greatly favors the actual ketone version, but remember at physiological pH, there's going to be a small amount of acetone that's going to exist in the enol form. So this would be the ketone version, or the carbonyl version. It doesn't always have to be a carbonyl, or it doesn't always have to be a ketone, but it's going to be a carbonyl. And then this is your enol version, right? And in reality, it's probably only about 0.01% of the actual species that's going to exist as an enol, but it does exist like that to a small amount, and it's in equilibrium between the ketone and the enol. So the equilibrium says that the tautomerization towards the ketone is greatly favored. And in fact, enols are terribly unstable. They're extremely high energy. So there's driving force to go to the ketone, which is lower in energy and more stable. So that's the driving force for the actual formation of imidazolone propionate in the carbonyl form, not the enol form. Okay, so I hope this video gave you a little bit of intuition on urocanate hydratase. The net effect is an addition reaction of an alkene, right? It's simple hydration of an alkene, but as we saw, the mechanism is not so simple. See you in the next video.